All right, we're going to work through problem 1.8 principally for the purpose of showing the representation of a number translated into the 64-bit IEEE 754 standard. If you can put one number into 64-bit representation, you can more or less do everything. So the problem reads, write the number 38.8125 in the following forms. A, binary. B, what is B? Base 2 floating point. And then C, 64-bit double precision string. So in A, the largest power of 2 that can be divided into 38 is 2 to the 5th. So this actually makes it fairly straightforward. You can do the left-hand side of the decimal in one binary conversion, the right-hand side in another, since they follow a separate summation. So you're left with actually the highest value being 2 to the 5th, but remember that is the 6th bit. 2 to the 0 is 1. That's a whole number, so you can't just ignore it. So in fact, 2 to the 5th, if you need examples on how to convert an integer number into binary, please go back one video and reference that. But the conversion there would be 100110. That's the left-hand side, and the right-hand side is 0.1101. And of course, that represents the presence of 2 to the 0, 2 to the 1st, 2 to the 2nd, 2 to the 4th, 2 to the 5th. Yeah, 5th, 4th, 3rd, 2nd, 1st, 0. Yeah, okay, we're good. And then on the decimal side, you had the decimal value of 8125. So this represents 2 to the negative 1, 2 to the negative 2, 2 to the negative 3, 2 to the negative 4th. Of course, not all of those count, only the ones enabled by turning on their switch, aka the little bit or the 1. So that's not a big deal. Like I said, if you want more detailed explanation, that's the previous example video. Go back and give that a watch. Should be a good enough example. Okay, so part B. Using the result of A, the binary floating point representation of the number is 38.8125 divided by the largest single base 2 number that would fit into it. So 2 to the 6th is too big. 2 to the 5th is 32 and fits just fine. So we execute that division of 38.8125 divided by 32. Of course, we have to multiply this again by 2 to the 5th. Otherwise, we're actually changing the number, right? But if we multiply the numerator by 2 to the 5th and the denominator by 2 to the 5th, we've done nothing to the number. We're just separating it out and changing its form. So in this case, that ends up being, putting this into the base 2 floating point representation, 1.212890625 times 2 to the 5th. I would really rather just tell someone 38.8125, but unfortunately that's not how computers work. This is actually a bit easier and more regimented way to represent a number as you work towards following the IEEE 754 standard. Because we now know our mantissa and we know the exponent value we have to represent in that IEEE standard. But to separate this a bit more cleanly, I've prepared a nice little Excel file. Now you'll notice that I have all the columns shrunk up to column BL, and that's intentional because that is the 64th column. If I highlight all these, you see that now I've highlighted 64C or 64 columns. That is the bit depth of a double precision number. The first bit, if you might remember, is our, let's go ahead and make this column shaded. You would think for a class on MATLAB I'd use MATLAB for this, but whatever, whatever works. And then the next 11 would be the exponent terms, and then the last 52 columns will be back to being the mantissa. So you can see the relative graphical container of information. So first question, is it a positive or a negative number? It's obviously positive, but the thing is you have to remember that 0 actually represents a positive number. So there's our first bit located and done. Exponent. We have an exponent value of 5. So if you went and translated 5 to binary, you would get the problem incorrect. You have to remember that there is the bias value of 1023. So 2 to the 11th is, let's look up on the handy dandy sheet, 2 to the 11th, 2048. So if you divide that by 2, you end up at roughly 1024, but there are reasons they don't go to the extremes. So you have 1023 as the bias. So adding that to the exponent, you actually need to represent the number 1028. So that number in binary form is it kind of makes sense if you think about it. You have the 1 representing 1024, and you add 4 to it. This would be the 1, 2, 4, 8, 16, 32, 64, so on and so forth, all the way up to 1024. So this is very reasonable way. The reason, again, that you have to put in the bias number for the exponent is that allows us to represent numbers that are very, very big and very, very small. You could have a number that's, e to the negative 20th. And by allowing you to have very, very small exponential numbers, this works out just fine. So now you represent the mantissa, which we've solved in the previous problem, as being 1.212890625, a very long number. Click the button here. There you go. The mantissa right down there. In fact, if you remember, no, I deleted it. Didn't mean to do that. What was the number? It was a 2. Okay, wrong button. That is the number we have to represent. Every binary system translation, after you divide a number by its smaller base to, not equivalent, but the next smaller base to whole number, integer number, will always be 1 point something. If it's 2 point something, you've selected the wrong base number. If it's 0 point something, you've selected the wrong base number. So that's why the mantissa can get away with just ignoring that leading 1, because it's always going to be a 1. Handy, right? So at this point, it would be rather a chore to translate 0.212890625 into binary. So let's just have the computer do it for us. The answer, once we do that conversion, is 0011011101. Of course, you know how to do this. If we needed to step back to the chart, I guess this is an example problem, so I should follow through with it. Let's put the example number out here, 0.212890625. In fact, to give myself some more room, because I know this will take a moment, we'll start there. So we obviously have nothing of the whole power. Are we greater than 0.5? No. Are we greater than 0.25? No, we are not. Are we greater than 0.125? Yes, we are. So we can take that number, 0.212, subtract out 0.125. We're left with that value. So you keep on stepping down. Are we bigger than 0.0625? Yep. I'm sure you could automate this in a much more elegant manner. In fact, that might be a good part of your homework. But for now, this works okay. Oh, I believe I made a mistake. We cannot fit 0.03 into 0.02. We can fit 0.015 into it, though. All right, 0097, 0078. Yeah, that'll work. 0019. I believe that's a no. Oh, hey, look at that. It's almost like the textbook made that match up perfectly on purpose. Now we're left with the remainder of 0, meaning that is the end result. So starting at the decimal level, the first negative exponent is 0011011101. Can't say that without thinking of Bender. And that's what we have representation there. So this in the 64-bit system, the rest of them would just be zeros. That is the IEE754 standard conversion of the value 38.8125. Good, wonderful. Well, there it is anyway. So following that same process, you can obviously see that the conversion of the mantissa into the 52-bit representation of precision is going to take the longest time. But seeing as how you're doing all of this on a computer, you're going to have a computer do it for you anyway, so who cares? Some gotchas might be that you forgot that a positive number has actually a 0 leader. If this was a negative 38.8125, you would change that to a 1. That's all that's required to switch between a positive and a negative value, except remember positive is 0, negative is 1. For the exponents, just remember the bias. I mean, if you forget the bias, the whole thing's wrong. And the bias for 64-bit is 1023. Other than that, that's the conversion. That should be a good example problem. We're done.